This is a M. So what we did is we have taken BN and AM be the perpendicular to OP we have been taken. So as it is making an angle theta here, so here also it is having the same angle theta it is going to be having. Theta is the angle it is going to be have here. Now we'll consider the potential P due to the charge plus Q at B. Okay, so now we'll consider the potential at P. That means at this point P, what is the potential due to this charge Q at which is located at the point P. So that potential we'll calculate here. So first we'll write the potential here. So here first what we'll do is now we'll take the take the potential at P, potential at P due to the charge plus Q, which is located at the B here. So that potential will take here. So that potential is given by, which is equals to 1 by 4 pi epsilon naught into the charge here, it is Q, and the distance is BP here will take BP. And this is also equals to 1 by 4 pi epsilon naught into Q by NP. This is also equals to this 1 by 4 pi epsilon naught Q by NP. Because this BP distance and this NP distance both are same, we have drawn perpendicular onto this one. Okay. So now similarly, we'll calculate the potential at the point A. Here we'll calculate. Now potential at point P due to the charge minus Q minus Q at A here also we calculate. So for that the potential you are going to get it as 1 by 4 pi epsilon naught into Q by the distance. Here the charge is minus Q, so it will be minus Q by the distance from P to the minus charge distance is AP, it is going to be happening. So it will be 1 by 4 pi epsilon naught minus Q by AP. And this is also equals to the normal which is drawn on to that one. So that is also equals, this is also equals to 1 by 4 pi epsilon naught into minus Q by MP, it is going to be MP. So here this one, this point P from A to on to this one, we have drawn the normal. So this will be equals to MP, it is going to be. This one is MP you have. So one is 1 by 4 pi epsilon naught minus Q by AP, and which is also equals to 1 by 4 pi epsilon naught minus Q by MP. Now, uh, we have calculated the potential at the point P due to the charge plus Q, which we have got like 1 by 4 pi epsilon naught Q by BP, otherwise, which is equals 1 by 4 pi epsilon naught into Q by NP we have got. And similarly, we have calculated the potential at the point P due to the charge minus Q also we have calculated, which is located at the point A. And we have got it as 1 by 4 pi epsilon naught minus Q by MP or Q minus Q by AP, both we can get. Now we will calculate the potential at this point P. Otherwise, we can say that the resultant potential we can calculate here. Okay. Now we'll calculate the resultant potential at the point P. We calculate here. Now the resultant resultant potential. Okay, a resultant potential at this point P we can calculate, given by which is given by cap V, which is equals to 1 by 4 pi epsilon naught is common. One is having Q by NP and another is having Q by MP. Okay, so this is the resultant potential at the point P due to both the charges plus Q as well as the minus Q, which we have got it as V is equals to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q by NP minus Q by MP, which we have got. Now we will consider here the right angle triangle ONB here. Okay. So here we'll consider the right angle triangle ONB here. So this is the center O we have, and this is the N, and this is the V. So because we have drawn the normal onto this one, so it will become right angle triangle. So first, from the right angle triangle ONB, we'll take some information, and as well as from the right angle triangle AMO also. So therefore, here we'll see that from the right angle triangle, from the right angled triangle. Okay, so the right angle triangle here is ONB. So from that we will take the value of ON, which will be equals to OB cos theta, because cos theta is equals to nothing but adjacent side by hypotenuse. So here it will become ON is equals to OB cos theta. And this OB is nothing but the distance from the center of the dipole O to Q, which is equals to A we have. So it will becomes A cos theta. So ON is equals to OB cos theta, which is equals to A cos theta. And from the figure, NP also we can write NP value. So NP is equals to OP minus ON it becomes. NP is equals to OP minus ON. So which will be equals to OP is nothing but from the center of the dipole to the point P, the distance, which is equals to, we have taken it as R minus ON we have calculated, which we have got it as A cos theta. So this is the information which we have got from the right angle triangle ONB. And similarly, from the right angle triangle, from the right angled triangle, okay, that is AMO. From this right angle triangle AMO also, we'll see here. We will take the value of OM, which will be equals to AO cos theta. Sorry, AO cos theta. That is nothing but from this figure. This is the right angle triangle here. It makes AMO. So from the figure, cos theta is nothing but adjacent side by hypotenuse. So adjacent side is OM. It is going to be from here to here, and this AM is AO is it becomes hypotenuse. So this is equals to AO. OM is equals to AO cos theta. So AO is nothing but the distance from the center of the dipole to the charge minus Q, that is A we have. So that will be equals to again A cos theta it becomes. Therefore, now we'll take the value of MP, which will be equals to MO plus OP. Okay. MP is equals to MO plus OP it becomes. So therefore, it will be equals to A cos theta plus R here. It is equals to A cos theta plus R. So from the right angle triangle ONB, we have got the value of NP, which is equals to R minus A cos theta. And from the right angle triangle AMO, we have got the value of MP as A cos theta plus R we have got. So these two values like NP is equals to R minus A cos theta and as well as the MP is equals to R plus A cos theta. These values we will substitute in this equation 1 so that we'll get the potential here. So now uh, substituting, 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 substituting the values of NP and this MP in in equation 1, which we have seen here. So we will get this if we substitute there, V is equals to, we have written already 1 by 4 pi epsilon naught into plus Q by, we have the value of uh, NP here. I'll show here. uh, NP, so which we have got R minus A cos theta, that we will substitute here. NP value. Let this balance here. Okay. So here we'll substitute that values so that we will get this V is equals to 1 by 4 pi epsilon naught into Q by, and that value of NP is equals to R minus A cos theta. So here we'll write R minus A cos theta plus we have Q by the value of MP is there. So that is equals to, we have got it as R plus A cos theta we have got. So one is R minus A cos theta, another one is R plus A cos theta. So now we'll solve this equation here. So if we solve this, here it is 1 by 4 pi epsilon naught into, so here in the denominator it will be R minus A cos theta into R plus A cos theta as we have taken LCM. So in the numerator it will be equals to Q we can take outside, so it will be Q by 4 pi epsilon naught. So here it becomes R plus A cos theta. So sorry, here it is not plus, it is minus. So R plus A cos theta minus R minus A cos theta it becomes. So it will be equals to Q by 4 pi epsilon naught. So in the numerator, so we'll get it as R plus A cos theta minus R plus A cos theta divided by R minus A cos theta into R plus A cos theta. It becomes R square minus A square cos square theta will be. So it will be equals to Q by 4 pi epsilon naught into, here this R get cancels. So in the numerator, it will becomes 2A cos theta by R square minus A square cos square theta it will become. So this V is equals to Q by 4 pi epsilon naught. This 2A is nothing but we can write it as a small p, which is a distance between the two charges. That is the length of the dipole. We can write it as a p. So it will be p cos theta by R square minus A square cos square theta. Okay. So simply we can write this dipole due to, sorry, elect potential due to dipole, we can write it as a P cos theta, P cos theta by 4 pi epsilon naught into R square minus A square cos square theta we can write. So this is what the potential due to the dipole at a point capital P we can calculate here. So this 2a cube, we can get it as a what we call a P small p, that is a dipole moment we can call. So here small p is nothing but that is a q into p, whichever we have like a 2a cube actually that is equals to small p, that is nothing but a dipole moment we can call here. So here we don't have this, erase this. Here it will be 1 by 4 epsilon, right? Here is a 1 by 4 pi epsilon naught into p cos theta square minus a square cos theta. So this is what the dipole moment, sorry, the potential due to a dipole moment here. Suppose here, if you consider the distance between the center of the dipole moment to that point P where we are calculating the potential is greater than A if we are having. That means R is nothing but the distance between the point P where we are calculating the potential from the center of the dipole is very greater than A if we are having. In this case, we can neglect the term A square cos square theta. A square cos square theta term, it can be neglected. So if you neglected this term, we will get this simply V is equals to P cos theta by, we'll get it as a 4 pi epsilon naught R square. This also we can get. The condition here is when we neglect the distance between the center of the dipole to the point P where we are calculating this one. So here, if you take this theta value is 90 degrees, if theta is equals to 90 degrees, that is nothing but the point P is located, suppose this point P, which is located normally from the center of this one. So if it is located at this point, then what will happen means the if theta is equals to 90 degrees, that is a perpendicular bisector of the line joining the charges if you are having. So it will become equilateral plane. So therefore, this value of V, it will become 0 because cos 90 is equals to 0. The potential due to the point will be equals to 0 here. Okay, so this means that no work is done by external agent in carrying a test charge from infinite distance along the perpendicular bisector of the dipole. So we have seen that potential is nothing but the amount of work done in order to move a charge from infinite distance to a particular distance within the field. We call it as a potential. So in this case, there will be no work done because V is equal to 0 if the condition is theta is equal to 90 degrees. So equilateral plane is equilateral line it becomes. So the potential of a dipole depends upon the dipole moment small p. As we have seen, this V is equals to P cos theta by 4 pi epsilon naught. It will be depends upon the dipole moment P, small p here, not on 2A or separation distance. So mainly depends upon this one. So once we'll reveal this, which we have calculated. So we have calculated potential, we have calculated due to dipole. So for that purpose, what we have taken is here, we have taken a dipole, which is separated by a distance of 2A. So we have taken the center of the dipole as O we have taken. So the distance between this minus Q to the center becomes A, and the distance between the charge plus Q to center becomes again A. Now we have taken a point P, which is located at a distance of small r, where we are calculating this electric dipole we are calculating. We have considered that point P, which is at a distance of small r we have taken. And we have joined the minus Q to P, and as well as this plus Q to this we have joined. And along this center of this O2, the distance, the point P we have extended in this side, and we have drawn the normal onto this one from the point Q to this one, which we have taken it as a BN normal. Another one is a AM normal we have taken, and we have calculated, we have written the potential at this point P due to this charge plus Q. We have calculated that we have got it as a 1 by 4 pi epsilon naught Q by BP. We have got, and that also we can write it as a 1 by 4 pi epsilon naught into Q by NP we can write. And similarly, we have calculated the potential point P due to the charge minus Q we have calculated, and that we have got it as a 1 by 4 pi epsilon naught into minus Q by AP we have got, and, which will be equals to 1 by 4 pi epsilon naught into minus Q by MP also we can write. So therefore, we can calculate the resultant potential at this point P we can calculate, and that resultant potential at the point P is given by V is equals to 1 by 4 pi epsilon naught into Q by NP minus Q by MP we have got here. So, which is the resultant potential at this point. Now, in order to know the value of NP and as well as MP, we have taken the right angle triangle initially, ONB we have taken, this right angle triangle we have taken, and then after we have taken another right angle triangle also we have taken, that is AMO. So initially in this right angle triangle ONB, we have taken the value of ON is equals to OB cos theta, and this OB is nothing but from the center to the point B, the distance we have taken as A, so it will becomes A cos theta ON value. So from that we can calculate this NP. NP becomes OP minus ON from the right angle triangle, so which is equals to R minus A cos theta. So NP value we have got it as R minus A cos theta we have got. And similarly from the right angle triangle AMO we have another right angle triangle. So from that right angle triangle we can take OM is equals to AO cos theta we can write. So AO is value is equals to small a, so which is equals to A cos theta we have written. Therefore, from the rectangle triangle only, we can write MP is equals to MO plus OP we can write. So MO is nothing but which is equals to A cos theta, which is we have taken, and OP is equals to plus R. So that is the value. So we have got the MP value as A cos theta plus R we have got, or as R plus A cos theta, and this NP value we have got it as a R minus A cos theta. So this MP and NP value we will substitute in this equation. One here we'll substitute so that we'll get the potential at the point P, which is a separated distance of R. So now the resultant potential, which is equals to 1 by 4 pi epsilon naught. So which is equals to Q minus, Q by R minus A cos theta minus uh, into Q by R plus A cos theta we have written. So which is equals to uh, we have taken Q outside, so it will be Q by 4 pi epsilon naught. So here we have taken the LCM R minus A cos theta into R plus A cos theta, so that we get the R plus A cos theta in the numerator minus R minus A cos theta. So if you solve this, we get it as Q by 4 pi epsilon naught into 2A cos theta by R square minus A square cos square theta we have got. And this 2AQ, so which is nothing but the dipole moment. So that we have written as a small p, dipole moment is small p. So it is equals to P by cos theta by 4 pi epsilon naught into R square minus A square cos square theta. So this is what we have calculated the potential due to a dipole separated by distance of R we have calculated. So if the condition is if the value of R is greater than A, if you are having, that means R value, the separation distance from the point P where we are calculating the potential from the center of the dipole is very greater than this A value if you are having, then we can neglect the term A square cos square theta, we can neglect. So that we'll get V is equals to P cos theta by 4 pi epsilon naught R square we can get here. This is what we have. Suppose if it is theta is 90 degrees we are having. So if theta is 90 degrees means the this is the dipole you have, and at this point P it will be there. So this is the perpendicular bisector. So at this point P, if you want to calculate the potential, so it will become 0 because cos theta is equals to 0. That means actually what actually it means the potential vanishes everywhere on the equatorial plane it is going to be have. That means there is no work is done by an external agent in carrying a test charge from infinite along the perpendicular bisector of the dipole. That is what we have. So this potential from this equation we can say that potential is always otherwise the potential of a dipole depends upon the dipole moment p, small p. The dipole moment small p, on that it depends and not on the separation distance to A or Q, how much charge it is present. So only depends upon the dipole moment. So this is what the electric uh, potential due to a dipole. And similarly, we'll move to this electric field. This electric field due to this dipole we can calculate here. 1 minute. Next, we'll calculate this electric field due to the dipole we can calculate. So now second part in this, we'll calculate the electric field here due to the dipole. Electric field at any point, at any point due to a dipole, due to a dipole will calculate here. Right. So here, which we are calculating electric pole due to a dipole in polar coordinates, we are going to be calculate. So that is the reason why we'll consider here r and theta both are polar coordinates of P. We are going to consider small r, comma theta. So these are the polar coordinates. Okay. Polar coordinates at P will take here. Okay. So now, as the figure will be same as this previously one, whichever we have drawn. So only the thing is we are calculating this electric field we are calculating here. Okay, electric field we are calculating. So the radial component of the electric field is given by ER here, radial component of electric field ER along OP, as we have seen OP where it is present. So that will be given by ER is equals to minus dou V by dou R we have, minus dou V by dou R we have. So this value ER is equals to minus dou V by dou R. We will substitute in the electric potential equation. So electric potential equation substitute we'll substitute in the electric potential equation. So now for this value of ER, we'll substitute in the equation of potential. Here ER is equals to minus dou by dou R of V. We have calculated the potential due to the dipole, which is P cos theta by so we have this P cos theta by 4 pi epsilon naught R square This is a 4 pi epsilon naught r square we have. So if you do the uh, partial differentiation to that one, so we'll get minus p cos theta by 4 pi epsilon naught this one, and this will becomes minus 2 by r cube we are going to get here. So therefore, this ER is equals to, we can write it as a 2p cos theta by 4 pi epsilon naught. Okay. So this radial component of electric field ER, which is the partial differentiation of this potential, that is a minus dou V by dou R. So we have got ER is equals to 2p cos theta by 4 pi epsilon naught into, here we have this called R cube, 2p cos theta by 4 pi epsilon naught R cube we are getting. So similarly, the transverse component we can calculate, uh, which is equals to E theta. That is a radial component. We have got minus dou V by dou R. Similarly, the transverse component of electric field, which is given by E theta, which is equals to actually minus 1 by R, minus 1 by R into dou V by dou theta you have. So it will be equals to minus 1 by R dou by dou T of V value. We have P cos theta by 4 pi epsilon naught R square we have. E theta is equals to minus 1 by R by dou T into P cos theta by 4 by epsilon naught R. So it will be minus 1 by R into, if you do the differentiation of that, we get it as a P sin theta by 4 pi epsilon naught R square we'll get here. So it will be minus sin theta here we'll get here. So it will be equals to, it becomes 1 P sin theta, small p it is, by 4 pi epsilon naught R cube. So this is the value of E theta, which is nothing but the transverse component of electric field. So here, if you see from that dipole figure, so actually dipole which is separated by certain distance, this one we have. So this is the center O. We are calculating certain point P electric field. So this is the distance. This is well, so from this, if you see this part, the electric field direction will be in this direction. We have actually the radial component is in this direction, which is ER, and the transverse component is in this direction. We have E theta. So the resultant will be here, which is E actually. This is the resultant E we have. So ER is in the direction of OP we have, and E theta is perpendicular to OP we have. So therefore, the resultant P here, which is given by, that is nothing but E value, we can say that resultant of these two, we are going to get it as under root of ER square, ER square plus E theta square. Okay, ER square theta, this one. So now we know the values of ER as well as the E theta. So ER we have got it as a P cos theta, 2 P cos theta by 4 by epsilon naught R, and E theta we have got P sin theta by 4 by epsilon naught R cube. So these values will substitute here, so that we'll get E value. So E is equal to root of this value is we have got like a 2P cos theta by 4 pi epsilon naught R cube whole square. That is E R square plus E theta square. So we have got P sin theta by 4 pi epsilon naught R cube whole square. Okay, whole square. So this, if you do the square, and if you take outside some part, we have P by 4 pi epsilon naught R cube we can take outside. So inside it will be 4P square as our P we have taken outside. So it will be 4 cos square theta, and here we have a sine square theta we have. So it will be P by 4 pi epsilon naught R cube. So inside it will be cos square, it will become a 1 plus 3 cos square theta it becomes. So this is what electric field intensity at a point P, which is at a separation distance of R we have. So this is what about electric field we have calculated, and as well as the potential we have calculated due to the dipole we have calculated. Okay. So next we'll see about the capacitance. Now we'll see about the uh, capacitance. 1 minute. Next we'll study about this capacitance. Next chapter, next unit we can study. So what is capacitance and what is parallel plate capacitance? You get what is the series combination, what is parallel combination also we'll see here. So now we'll study about this the capacitance. So we have studied about the uh, potential of a charged conducting sphere we have seen with a radius r, which is having a charge of q, which is given by actually the potential. This potential is given by v is equals to uh, 1 by 4 pi epsilon naught q by r we have. So this r is nothing but the radius of the sphere we have, and the charge on that will be equals to q we have taken. So this is the potential v is equals to 1 by 4 pi epsilon naught q by r we have taken here. Suppose the line marked as a v infinite, which represents the reference position where the potential is assumed to be 0. So therefore, we'll get another potential for negative charge. So this is actually for the positive charge. If we take, it will be V positive 1 by 4 pi epsilon naught q by r. Suppose if it is a negative charge, if we are having, then we can write 1 by 4 pi epsilon naught into q by r we can write. So which is minus, we are going to get minus 1 by 4 pi epsilon naught q by r. So suppose if you want the resultant potential due to the positive and negative charges, it will be V is equals to V plus minus V minus you are going to get. So this if you do, you'll get it as a 1 by 4 pi epsilon naught into 2q by r you are going to get here. So this here q value you are going to get it as from this equation as 2 pi 2 pi epsilon naught r into this v you are going to get. So which is nothing but this 2 pi epsilon naught r is nothing but c value, which is capacitance we are going to become. So q is equals to cv. Okay, so this 2 pi epsilon naught r is nothing but the capacitance of the two spheres, and is which is represented by C you are going to be have. So therefore, the capacitance from this equation we can write it as C is equals to C, the capacitance from this we can equation we can write it as C is equals to Q by V we can write here. C is equals to Q by V we can write here. So this capacitance we can define as otherwise we can write this capacitance as the ratio of the magnitude of the charge Q on either conductor to the potential V between them. Okay, so the definition of the capacitance we can write it as the capacitance is the ratio of the magnitude of the charge Q on the either conductor to the potential V between them, we can write here. Okay. So if the value of potential V is equals to 1 if you are having and C is equals to Q, hence the capacitance of a conductor may be defined as the charge required to raise its potential by unity, we can say that. So that is what we have. So generally the capacitance which we can measure in terms of farads we can measure. So which is the unit of the capacitance. So generally we have like a 1 microfarad is nothing but which will be equals to 10 to the power of minus 6 farads we can consider here. And similarly, we have like a picofarads will represent in terms of 1 PF. So generally, 1 picofarad is nothing but 10 to the power of minus 12 farads we have. Okay, pico nanofarads is nothing but 10 to the power of minus 9 we can take here. Okay, so that is the capacitance and the units of the capacitance we have. Okay, so now we will move to what is actually capacitor. What is actually capacitor? What is capacitor? Let's see here. Next, we'll study about what is a capacitor. So, actually, the capacitor is nothing but the considerable amount of charge, which is called as a condenser or capacitor, we can call. So, otherwise, we can define this as a device for storing the energy in the electric field between the plates, we can say that. So already we have studied about a conductor. So if a conductor is placed near a charged conductor, the potential of a charged conductor decreases and hence it can store more charge. So the arrangement of two conductors that are placed close to each other and isolated from each other is known as capacitor. So here, if I'll show one example, so this is having the positive charge on this one. So another one, it is having the negative charge. So the potential of a charge conductor decreases and hence it can be stored more charge. The arrangement of two conductors that are placed close to each other and isolated from each other is known as what? Capacitor actually. So the capacitor why we are going to be used is, we can say that it is a device which can store certain amount of energy in the electric field between the plates you are going to be have. So as I shown that here, if it is having a positive charges, so like this here, if the two plates are separated by certain distance A, B, so inside of this, uh, all these charges will be located. So energy will be stored here. So generally, if we are having n number of capacitors, so if n number of capacitors are connected in series, we already know. So the resultant capacitance of that capacitor is given by 1 by the, if they are connected in series here. So the resultant capacitance is given by 1 by C is equals to 1 by C1 plus 1 by C2 and so on to 1 by Cn, as we have taken n number of capacitors if they are connected in series. So the reciprocal of the effective capacitance of a number of capacitors connected in series is the sum of reciprocals of their individual capacitances you are going to be have. Okay. So then suppose if they are connected in uh, parallel, if they are connected in parallel, that is nothing but if you are having a parallel connection. Parallel connection. Suppose if you are having n number of capacitors are there and whose capacitance are like a C1, C2 and up to Cn if you are having, these are connected in parallel. Then in this case, the resultant capacitance is given by C is equals to C1 plus C2 plus C3 and so on up to Cn you are going to be have. So this is the resultant capacitance of a parallel connection. Okay. So this is about the capacitance if you are connected in a series and if you are connected in a parallel. That is what we have. Okay. Now, capacitance of a concentric spheres we have to see here. Capacitance of a concentric spheres we can see here. Okay, today, so far what we have studied is here. So we have first we have calculated the potential and electric field due to the dipole we have calculated. So initially we have calculated the potential due to dipole we have calculated. So for that purpose we have taken one uh, dipole AB we have taken, and the center of the dipole is O we have. The distance between this minus Q to the center is O, and the so O to Q is again A we have. So at this point P we have to calculate actually the potential, which is at a distance of R. So that we have taken the potential P at the point B where the charge is Q, that we have got it as 1 by 4 pi epsilon naught Q by NP, and the potential at this point we have got it as another point we have got it as a minus Q by MP. We have got 1 by 4 pi epsilon naught into minus Q by MP. And the resultant potential we have taken here, that we have got it as a 1 by 4 pi epsilon naught Q by MP minus Q by MP. And we have taken the right angle triangle, so ONB and AMO. We have calculated the NP value, MP value. We have substituted, and so that we have got potential is equals V is equals to 1 by P cos theta by 4 pi epsilon naught into R square minus A square cos theta. And if the value of R is greater than A, we can neglect this A square K cos square theta. So resultant potential we have got V is equals to P cos theta by 4 pi epsilon naught R square. So if theta is equals to 90 degrees, that is a perpendicular bisector. So V will be equals to 0. So that means there is no work done in carrying perpendicular. So electric field also we have calculated. In order to calculate the electric field at that point, we have taken this polar coordinates r comma theta. So radial component of electric field is given the minus dou v by dou r. We have substituted the v value so that we have got the er value. And similarly, the transverse component is e theta, which is equals to minus 1 by r into dou v by dou theta. So we have taken the partial differentiation of this one, and we have got er is equals to p sin theta by 4 pi epsilon naught r cube. So the resultant E will be equals to the square root of ER square plus T theta square. So we have substituted, and we have got this as P cos P by 4 pi cos 4 pi epsilon naught R cube into this value root of 1 plus 3 cos square theta. That is a electric potential we have got. And similarly, we have studied about the capacitance. What is capacitance is C is equals to Q by V. That is the ratio of charge to the potential. And the units for the capacitance we have seen, like 1 microfarad is equals to 10 to the power of minus 6 farads, and 1 picofarad is equals to 10 to the power of minus 12. And the series combination of the capacitance is given by 1 by C1 plus 1 by C2 and so on, 1 by Cn for any capacitors of having the capacitance of C1, C2, and so on. For a parallel combination, it will be equals to C is equals to C1 plus C2 plus C3 and so on up to Cn. So this is what about the capacitance. So in the next class, we'll study about the we'll calculate the capacitance due to the concentric spheres we can calculate here. Okay. So as of today, we'll stop this class here.